Welcome to my amazing state-of-the-art laboratory where the future of food is being built. Well, not exactly. This is my real lab. It may look less glamorous, but this is where real science happens. All my life I've worked with yeast and fermentation, from baking yeast to astaxanthin, both leading to patents, and even fermented olives, where we developed a published post-harvest treatment. And this is me, a PhD student. And this is my supervisor, Professor Ficshman. Together, we use yeast to create sustainable plant proteins with commercial potential for the future of food. Today we focus on one yeast, Pichia pastoris, a powerful fermentation system for alternative proteins. But why do we even need this? Global protein demand is rising fast. Traditional agriculture, meat, and dairy consume too many resources. We need sustainable solution. And yeast fermentation can provide the proteins of the future. To get started, we needed to build a protein production platform. To do that, we went through a series of key steps. First, we formulated a new fermentation medium. It took a lot of effort to optimize, but it enabled record biomass, over 160 grams per litre in just 30 hours. We compared 3 different wild-type strains on glucose and glycerol. In the graph, you see just one example. But across all strains, glycerol performed better. Using it in our optimized medium, we reached 240 grams per litre, the highest biomass reported so far. The next step was to test the platform with a model protein, M-cherry. We stably integrated the M-cherry gene into the Pichia pastoris genome, so the protein wouldn't be lost, and compared the 3 wild-type strains for their ability to produce protein. We also created diploid versions of these strains and compared them to haploids. This showed us which strains and ploidy levels were the most promising. Strain Y11430 had the highest potential, and the diploids consistently produced more protein than the haploids. This was the first time diploids were tested in Pichia pastoris for protein production. You're welcome to read more about this platform in one of our published papers. Then we applied the platform to a real food protein, napin from rapeseed. Napin is a valuable seed storage protein, but extracting it from press cake, the residue after oil extraction, requires extensive purification. With our platform, we expressed recombinant napin in yeast using 2 promoters, GAP, a constitutive promoter, and AOX1, induced by methanol. The GAPI promoter increased our napin yield by 2.4-fold in haploid strains. We also tested diploid strains. Diploid expression led to an additional 1.5-fold increase. After purification, recombinant napin showed higher solubility across pH values and better emulsifying activity under acidic conditions than napin purified from rapeseed press cake. This study was published. After napin, we're now applying the platform to patatin, a major potato protein, testing both secreted and non-secreted production. And this platform goes far beyond these two. It can be used to produce many other valuable proteins for food and beyond. And this is me again, trying to save the world, one fermenter at a time. Thank you for listening.